Hello, I'm Jim. I work for ThoughtWorks, and for about a year or so now I've been getting more and more interested in this thing called blockchain, and so I thought I'd have a go at explaining it to you guys. It's quite fascinating, and we're going to go into a kind of magical world. There's some quite strange things lurking in this forest. So, in case you missed it, the world has kind of gone a bit blockchain crazy. To the point, it's also changing very rapidly. So this was like in August or something. This year, just now, came out. The World Economic Forum. Hillary Clinton has even mentioned it. The chief scientific advisor for the UK government has made a whole paper about blockchain. It's even been on the Today programme in the morning, driving to work. So that's quite big, which has led to a lot of investment in startups in blockchain. A lot of money and people being interested. So what is it? Well, there's two things you need to know about blockchain. The first thing is that it's awesome. And the second thing is that you can do anything with it. It can be applied to anything. And that's kind of what you hear when you see some of the talks and see all those startups, because that's what they're doing, right? They're trying to sell this thing. And that's a bit like Linda's talk at the beginning. So for this talk, we're going to go into the blockchain forest, set a couple of expectations. I'm not so much going to be talking about why blockchain's so awesome and why you should just go and buy it or invest in a blockchain startup or whatever. I thought it'd be a bit more interesting to explain a bit about how it works underneath. So that's the thing that kind of caught my imagination. I was like, oh, that sounds great, all these great stories. What is it? How does it actually work? So we're going to go on a journey into this magical forest. And along the way, we're going to meet several different denizens of the forest. And before we start, I thought it might be worth trying to find out kind of like where everybody's at in the audience with familiarity with this, so I can kind of sort of judge how much detail to go into. So I thought a good way to do that would be hands up if you understand all of the things that are on that screen. You've heard them before, you know what they are, and you know how they work. That's good. So we've got some good experts in the audience. So you can help me and keep me guided if I go off path in the forest and say something that's completely not true. It's quite confusing in there, and so it's taken quite a long time for me to get to the point of being able to explain it and take you through the forest. So it's my first time, so we might get lost. So we're going to meet some of these things. One interesting character, so a lot of blockchain comes from Bitcoin. Has everybody heard of Bitcoin? Right, good. It's a good starting point. And the entity which wrote the original Bitcoin paper and code is called, how does this work? Satoshi Nakamoto. And nobody knows who he is. It's a pseudonym, a pseudo-identity. Nobody's found out who it is at all. So the mystery starts just right there. And continues with some of these other strange things, including marmots, which we'll get to meet later. They're very cool. Before we go into the forest, we're going to need to take with us some items, mental items, not insane, in our head, mental tools. The first thing we need to know about is cryptographic hash functions. So everybody know what a cryptographic hash function is? Good. Yes, the techies. Don't worry, for those who don't, I've got a quick demonstration of that. The second thing we need to understand about is Merkle trees. Everybody Merkle trees? Yes, that's back to the people who knew all the things before. Not that kind of Merkle. So we'll see what those are. And then the final thing we kind of really need to know about is digital signatures. That's public key cryptography. If I say those words, does that everybody happy with that? Does somebody tell me what ECDSA stands for?
Elliptic curve,
come on.
digital signature.
Yes, nice. I'm not going to go into elliptic curve cryptography, although that's very interesting. It's another talk in its own right. So we're going to look quickly at what that does and how does it relate to blockchain. Cool. And this is where the Bluefruit guys come in. So one thing that's I found when you start looking into all this, it kind of helps if you kind of know quite a bit about how to do your bits and bytes. And as we saw from the previous talk, understanding kind of like C and the way, and your big endian from your little endian and your hexadecimals and all of that. You don't need it for this talk. But in general, if you're interested in researching it more, it helps if you know your bytes from your bits and how to do all that stuff. So cryptographic hash function, quickly. What am I doing? That's good. We've got 5 minutes to do the tools, and then we'll see if we can get in the forest. So just briefly, what you can do is take anything, some text, some bytes, some bits, and you kind of like crunch it all up in through a very complicated mathematical function that's called a one-way hash. It's a bit like a shredding machine, and then you compact it into a series of bytes. And that makes it very difficult. It's impossible, in fact, to reverse engineer that, to take a series of those bytes and work out what it was that was in there, where it came from. So, for example, I can take the entire works of Shakespeare, which you can download from there, and you can run it through a hash function. This one happens to be called SHA-256, which is a common one. It's the one that Bitcoin uses. And you get this very long, I think it's 64 characters thing, code, hash. Everybody happy with that so far? The interesting thing about it is these mathematical functions are very sensitive to small changes. So if I just changed the first letter from a big T to a little t, and I get a very different function, a very different output, which is one of the reasons why it's very hard to reverse engineer. So the cool thing is they're very repeatable. So I take the same input, I take the same function, and I can run it on any processor, any language, and it'll give me the same thing. So they're very reliable ways of knowing a particular set of input data. And it's kind of easy to do. You can do it everywhere. It's not new. Okay? So you can do that in any language you like. Second thing, digital signatures. Now, the main thing about this is you've got some kind of input which goes through another kind of mathematical function, some magic in the forest, which creates these two things which are connected together. You've got a private key and a public key. And what you can do with those is you can take one of these hashes that we saw before, and you can, what we call sign it, which is another kind of cryptographic function, and create a signature. Now, the clever thing about this is that the signature that I created with my private key can be validated by somebody with my public key. And this is basically how the internet works. So HTTPS certificates and all of that, that's how the internet works. What's great about it is I can keep this. This doesn't have to go anywhere. It can be on my phone. In fact, there is one on my iPhone in a hardware module. And I don't have to give it to anybody, but I can make this as public as I like. I can print it on the front page of the Independent or whatever. And that allows anybody who knows they've got a good version of my public key to validate anything that I give out. So I can write a message, I can sign it with my key, and then any of you guys can validate that it was actually me who did it, because I'm the only one who has the private key. Okay? Everybody good? Cool. Merkle trees. So, let's say we've got a set of data, or data items. These can be anything, bits of text, JSON files, whatever you like. What we do is we make a hash of each one of those data items. We then take the hashes and hash them together and make another hash. See how it's starting to look like a tree? And then you do that again, and you do it again. And in the end, you get this thing at the top, which we call the Merkle root. And what's cool about this is it allows you to take a very large amount of data and reduce it into sort of a much smaller subset of things which can be validated. So if I wanted to check that this piece of data actually belongs to the data set which I'm publishing, all I have to do is provide you with this hash and this hash and this hash. There's a way you can do that. You only need a few pieces of the information to be able to validate that that data belongs to that data set. So it's kind of a useful way of compacting the validation of all those things into a simple way. And it also helps if you want to kind of like move data around. So that's basically saving you from having to take all the data, like the works of Shakespeare, and put it all into one big hash. So it's a kind of optimization. But it's kind of right in the middle of the blockchain. Everybody cool with that? Don't need to worry too much about Merkle trees. So that's good. We've got everything we need. Before we go into the blockchain forest any further, there are a few things that are a bit like blockchain, but aren't quite. And some people might not like being referred to them as blockchain. So one of the things that, and these things are kind of already out there as well. So yeah. So the first thing is we quite often use it for log integrity, distributed logs, and we Merkle tree things up, and then that's a good way to validate the data. There's this thing which is quite interesting. So I don't know if anybody's seen this, the open register stuff that government is doing, GDS are doing. It's all about publishing lists of things and making them verifiable, and they're planning, or one of their implementations uses Merkle trees to validate the data. And Google have this thing, certificate transparency, which is a way to validate that your certificate is real and has been registered somewhere. And that also uses Merkle trees and hashes and all of that. Cool. Some other things that are blockchain. So this is a brief intro to some of the applications of blockchain that are out there. So there's Bitcoin. We're going to look at Bitcoin in a minute. There's this thing, Forevermark. Has anyone heard of that? Thanks, Mark. I got that earlier. And that's for tracking diamonds. That's quite a nice one to look up. That's quite interesting. There's this thing. We'll talk a bit about that later. Ethereum. You might have heard of that. Did anybody hear about the DAO hack distributed? Yeah, that's quite famous blockchain news. I've got a bit on that later. The Swedish Land Registry are doing a trial in which they're using blockchain to sort of validate title registrations. There's some other excitement around Land Registry. I'm working at the UK Land Registry at the moment, which is one of the reasons why I started getting interested in this. There's a thing called Ripple, which is all about doing settlements across banks, between banks in international things. And NASDAQ have been using it in an experiment to do kind of automated trading. So that's sort of the kind of scene that it's being used in. The finance sector is particularly excited about it. Well, excited stroke scared about it. So, Bitcoin. Good. What is it? It is this. Is everybody pretty familiar with Bitcoin? Does everybody get the sort of premise of Bitcoin, which is essentially that it's like money, but nobody owns it. So this thing, like the money that we have in our pocket, is a fiat currency, which is owned by a government and backed by the government and all of that. This isn't really a real currency in that sense, but it's just something that people believe has worth, like gold. So it can be traded. But the massively important thing about it is that it's distributed and nobody owns it. So everybody who's participating owns it. There's nobody in charge. Sounds a bit crazy. But that's one of the most interesting parts about it. So here's a few sort of summary things that are important about Bitcoin. It's kind of very public, so you can download the entire Bitcoin blockchain onto your laptop and see it. Everybody can see it. It's, in theory, immutable in that you can't change it, but it's more right to say that you can't change it without anybody noticing, I think, is a better way to do it. It's kind of peer-to-peer, so we'll talk about that in a minute. It's also algorithmic. That's quite important. So it's like there are rules, but those rules are executed by computers. There's no humans involved, which means that you don't have any intermediaries. So in financial transactions, there's always some intermediaries, right, like the banks or sort of the exchanges, stockbrokers, whatever. And in this world, you don't need intermediaries because everybody trusts the system, and it's distributed. Maybe we don't need banks. That's one of the dreams. Maybe we don't need banks at all. We'd just all be happily working on Bitcoin. I wouldn't put all your house money into Bitcoin right now. It's a bit volatile. So, if you want to know some more, I found this book really useful. Again, even this guy is kind of mysterious. He doesn't seem to have much of a footprint if you try and look him up, but it's a really good book, and it's got a lot of technical detail in there as well. Okay, just have a drink. Ooh. So, as I said, Bitcoin is a distributed network. So there's these nodes, machine computers, and they're talking to each other. And basically, you can put transactions. So in Bitcoin, a transaction is there's Bitcoins, and I can transfer them from me to you. That's fundamentally what I can do with them. And so I can submit a transaction to any node in the network, and the nodes all talk to each other and agree, and we call that consensus, coming to a consensus on what the truth is, and they store it in what's sometimes called like a ledger, which everybody agrees is the truth and is persisted across all those nodes, which is good. And this isn't a particularly new thing, distributed computing and shared data and all that. And we have some kind of tools and things. I don't know, has anybody ever tried to understand Paxos in detail? Yeah, it's not, yeah. You're still all right. Yeah. And there's a later sort of version, Raft, and that's used in kind of like distributed databases and things like that. So that part, so far, nothing that we've seen is really that new, right? It's all kind of been around for ages. And that's kind of the clever thing about Bitcoin is Satoshi sort of brought all these things together for the purpose of building this thing that didn't need any trust to work. But wait, what if everybody's not playing the game in the same way? What if one node is being deliberately malicious, right, and putting out fake transactions or trying to subvert the thing? So this is the sort of at the core of how could you have a networked system with lots of people participating in it and nobody in control, right? In a bank, they would say, hey, that person's doing the wrong thing, stop them doing the transaction, cut the transaction out. And this is where we come to another of the characters in the forest, these Byzantine generals. They'll appear several times throughout the talk. So this is referring to a problem where there's some generals in the Byzantine era, and they're trying to communicate with each other, and they can't trust each other. One of them might be lying or whatever. And so how do they know that the messages are true or not? You don't really need to know the full details of that, but it's quite an interesting story if you want to look up. So we refer to this, that's why we get this name, Byzantine fault tolerance. So we're trying to design a network that can still be good and true, and we can still know what the right answer is, even in the face of one of the nodes behaving maliciously. Right, that's good. So, Bitcoin, how does it work underneath? I think we've got everything we need now to understand it. So, roughly, we have transactions. Transactions are made up of essentially an input and an output. So it's where's the money come from and where's it going to. And this works safely. There's this thing which is a fee. So we're not going to go into that too much, but the people who are running the network get paid in Bitcoin, so they can collect a fee for every transaction they process. We'll see why in a minute. And these are kind of joined together. So, and this is where our private-public key thing comes in. So in this transaction, the person who created this transaction is saying, I would like to give this amount to the person who has this public key. And that's basically an address in Bitcoin, a Bitcoin address. So the person who has this public key comes along and creates a new transaction. They can now spend that. Let's say it's 10 Bitcoins, and I want to give it to Toby, and I'm B. I come along, and I create this. This is just a piece of data. And I sign it with my private key. Okay, remember that part? Which is that. And I say where I want it to go to. So I say where I want it to go to, that's Toby's public key, and then I sign that whole thing. So now, only I could have created that message, right? Unless somebody stole my private key, which is a hazard to be aware of with Bitcoin. Don't lose your private keys. And basically now, everybody can check that that transaction is good. And so all those nodes can all verify that transaction is good, assuming they're all behaving sensibly, right? Making sense? Where's the blocks? Right, so you've got these transactions, you've got a lot of them, they're floating about in the nodes, and so you have these things called miners, who are sort of the ones who create the blocks, and they're looking for transactions. They take a lot of them, and they build a Merkle tree of them. So we're kind of familiar with that now, right? It's going a bit fast, but don't worry. Once we've got our Merkle root, we can then take the hash from the previous block, and that hash them together, and we get the hash for our current block, which is basically where we get the chain from. Okay? But wait, what about these guys? How do we stop somebody just making up their own chain, putting their own transactions in it, and then creating their own blockchain, and then everybody would just agree that that was right, right? So this is where the kind of clever part comes in. So as well as making that hash, we have a special game we have to play, which is the hash. So these hashes, remember, they were quite random, right? You just put your data in, and you don't know what's going to come out. You run it through the hash function, it comes out with something. What you can do is say, I'm only going to accept hashes that are below a certain number. In maths, it's like a numerical number, but it looks like when you write it in hex, there's a certain number of zeros on the beginning of the number. That's all you kind of need to know. And this is a sort of random process. The only way you can find these is to basically take random numbers or a sequence of numbers, go through them like 1, 2, 3, 4, 5, add them to your hash, hash it, and see does it have a 0 on the front, or is it lower than a certain value. And we call that the nonce, which we'll do a quick demo of. So there's a bit of Python which does this. And basically all it's doing is taking a message hash. It's going to look for things that have 1 0 on the end because it's very quick. Okay, that wasn't hard, right? It took like 10 goes to find one because it only needs one thing on it. If we change that to, well, I'll do it to 5 straight away to save time. Will be some time trying to find it. So what's that saying is, in order to locate that hash, in fact, we'll probably never find it, so I'll just stop that. I have to use some power on my computer. It's running processes, right? It's searching for those things. And that's what we call mining. And it's also called proof of work. So by the fact that I've found this hash, the only way to find that hash is to spend some cycles on my computer, which takes some time. Currently, in the Bitcoin network, it's about 10 minutes, roughly, between each block being mined. So let's go back to the... So we now have, we're getting close to the full Bitcoin blockchain. We've now got this nonce. The thing about this is it's very easy to verify. Remember that hash function? It's very easy to take the input, run it through the hash function, and see does it produce the zeros. It's just very hard to find one that has a certain number of zeros. I think, we'll look at one. Right? So this is a recent block. You can see there's like, I don't know, 10 zeros on the beginning. That's going to take a lot of processing, right? And then the miners have all special kind of GPU processors that are especially good at finding doing hashes and running through a lot of numbers. So we pretty much have everything we need to know about these things now. So you see some of the things. So there's this difficulty. That's just a number it has to be lower than. We've got the nonce. We've got the Merkle root. Should all be quite familiar. Got transactions. The block height is the number of blocks in the chain, which is about that. So that's like the first block, then 1, 2, 3. But what about these guys? Again, even though I've got all that proof of work, so the basic point is how do we stop people faking this chain, right? And the principle is that because it takes a certain amount of time to mint one of these blocks, right? If you wanted to go back in time and reverse all of those blocks, you'd have to be going faster than the blocks are being added to the end, right? And that's going to be pretty much impossible. You'd have to have like twice as much computing power as all of those nodes in order to be able to keep up and rewrite history, basically. Maybe you want to double-spend your money and pretend that you've sent it to somebody and not actually sent it. The other thing that can happen is that because all of these miners are just building blocks whenever they want to do, sometimes you might get 2 blocks at the same time. That's called a fork. And the rule is quite simple. Just follow the one which has the most things on the end. And what will happen is by natural stochastic things, it's very rare that that will survive, because sooner or later somebody will be building on this block, and then there'll be 3, and you'll follow that chain. Okay, don't need to worry too much about that. The main point is that it's very hard to fake it. In fact, it's near enough impossible that people say that it's immutable. So you've got all these blocks in a chain, and in order to reproduce that chain, you'd have to spend, imagine faking it, you'd have to spend all, you know what I was doing with the computer there, I'd have to have all the computers that are in the current block. I don't know, Marcus, do you know how much the current gigaflops or whatever it is of the Bitcoin network? It's pretty big, right?
It's fascinating to see, I guess,
Yeah.
Like something like raised at 5 or 10%?
Yeah, and a lot of power. This is one of the problems with Bitcoin, but we won't go into that. So it uses a lot of power to do it. So we're good with Bitcoin. That's the basics. That's your basics intro to what blockchain is. I just want to rewind a little bit. There's something about this which is interesting. Although this is a lot about data, and it's basically kind of storing a sort of database of transactions, there's something else going on. There's some rules happening here, right? And in fact, in the Bitcoin network, the way that this is calculated is actually kind of like a mini computer running inside there. And it's just got a very specific function. Its only job is to check that the inputs match the outputs and that a transaction fee is paid, and that all of this signature stuff is all valid. So there's a bit of logic being executed. It's kind of like a distributed computer. And this is where the sort of blockchain thing started, really. So we've got Bitcoin. That's been running for quite a long time, 8 years or so. And people started realizing that actually you could start doing other things with this, maybe not just currency. And so we have this project called Ethereum, which basically took that concept and expanded the bit where the logic is executed and turned it into a more general purpose computation engine, like a virtual machine. So all the same stuff, the hashes, the blocks, but when it goes to execute a transaction, you can basically write some code in there, and they've created a language for this code called Solidity. Now there's some interesting issues with Solidity at the moment, which we'll look at later. But essentially it's a way of writing some rules about how you want your transactions to run. And it's kind of a Turing-complete language. We'll look at some in a minute. That's the next part of the talk. Cool. So I kind of think that what's happening here is that we are commoditizing some of these things, like the fact that we want to be able to know that a particular transaction was made by a particular person, or that we want to be sure that everybody can share the same thing. We could write custom code to do that, but this is offering us a way of making that in a very standard way. Yeah. And something very important about this, if you think about it, the next thing that really is massively important, I've got these keys, these digital keys, right? I can create them anywhere. And one of the things that people kind of a bit unsure about with Bitcoin is you can't really tell who's doing what on there, right? And in fact, that's how it got a lot of use on the Silk Road, illegal use. Basically, I can create that. Anybody can create a key, and it's not tied to my identity. So at some point, and this a lot of the banks are thinking about this, you've got this problem of, I want to do these nice digital transactions, but how do I know who that actual person is? So identity is still, that's a whole different forest. We're not going to go in there this time. But it's an important thing to know. Kind of like, so what, right? That all sounds, maybe it sounds quite exciting. It's quite technically exciting. There's lots of magic and strange things going on. But why? What's so cool about it? And I suppose I was asking myself the same question. And then I was thinking about a particular scenario, and I suddenly kind of started thinking about, okay, maybe I can start seeing why this might be useful. So I'm going to kind of try and show you what that scenario was and see if you kind of think it's also useful, and you can kind of make up your own mind. And in order to do that, that's where we get to meet the marmots. So one of the things that's going on in all those startup companies is people are trying lots of different things to make money out of this blockchain, right? And these guys, this Eris company, are building a kind of tool set on top of the blockchain underlying technology, which makes it easy for you to manipulate blockchains. So if you want to experiment a little bit with it, this is quite a good tool set to use. I've been using it for the last few months, and they've got a pretty good community. They're quite responsive, very responsive actually, and they love marmots, which is quite cool. The guy who started it does a lot of talks involving marmots. So, this is a bit of an experiment that Alan and I were talking about earlier. I don't know if you might be able to, I tried it earlier on my phone, it didn't seem to work, but the code is up there, so maybe you can use your things to access it. I'll put that up again at the end. Cool. We've got 15 minutes, that's good. Everybody tried, does it work? All right, cool. Yeah, so I'm probably going to work on this after this, so there might be some updates there. There's some other tech. All these are kind of like implementations of blockchain, which is sort of a bit like Bitcoin. So they do all that stuff with the hashing and the blocks and all of this and different transactions. People are standardizing on this Solidity as a language, this virtual machine, so that's kind of useful. And there's a couple of things that aren't so rosy about this whole world. I actually am running a little bit low on time, I think, so I'm not going to go into that too much detail. But one thing you do need to be aware of, so nobody's really corrupted the blockchain itself, the Bitcoin blockchain, but people have stolen Bitcoins. Like, they've broken into the people who do the exchange between Bitcoin and the real world, and they've stolen loads of private keys. And that's the problem with that private key thing, right? If you steal my private key, you've got all my money. You've got all my Bitcoins. Oh. I think I'm missing a... Right. So, I'm going to show you this thing. So, first of all, we're going to look at just what this Solidity, this contract thing is. So they call it a contract. It's called a smart contract, and it's basically this sort of bit of executable code that executes as part of the process of building those blocks up, right? And it looks kind of familiar. It looks a bit like sort of JavaScript-y, with a bit of C maybe thrown in. It's a bit of Golang-like as well. But yeah, anyway, but it's basically a language, right? You can see it's got if statements, it's got functions. You can have, where's my thing? You can have state. You can set the state. You can execute methods on it. Methods are executed by sending a transaction, a bit like the Bitcoin transaction, into the blockchain, right? So let's say I want to set this value. What I do is I create a transaction which says, please set the value of 33 into the field A or whatever, to this function, call this function with these parameters. And my client will sign that in the same way that we saw with blockchain, with my private key, and it will get added into the block and then processed. In this implementation that we're going to use, they're using an engine called Tendermint. That doesn't do that fancy searching for the magic block number. I'm not going to go into that. There are different models of consensus. It gets quite complicated, so we're not going to go into that. So, again, kind of like what? That's great. That's like that's just like a program, isn't it? Right? What's so cool about that? So what I started thinking about. Ooh, I was trying to move screens with my clicker. That's not going to work. Let's take a real-world scenario. So I'm like a bank or somebody, and I'm trying to create loans and give them to people. And involved in that, there's the lender, there's the bank, there's the people who are borrowing this thing, and also I've got these counter-fraud people who really want to make sure that the transactions and the people involved in them are really good, right? And it's all digital, so there's no paper involved. So I know that my borrowers have through some identity mechanism, which hasn't been invented yet, maybe it's my iPhone or whatever, have a private key which they can sign the transactions with. So what I want to say is like a mini program that says, here's the contract, and when the borrowers have both signed it, or however many borrowers there are, then the counter-fraud people are going to also have a look at it, and they're going to sign it. And then when they're happy with it, it's kind of like approved. So we've got this sort of state. So you created, the borrowers have signed it, it's ready to pay, that's like fraud have approved it. And then the bank is going to do the transaction, pay the money, and then they're going to sign it, and then it's going to be marked as active. Making sense? And that's roughly what this does. And it gets, it's quite deep, this language. You get in your mind around how it works. But essentially, you can kind of do things like put constraints on it. So you can say, this initialize function can only be done by the person creating the contract, the executor, that I've called it in this case. Some of these things, there's special things like this address, which is like one of the public keys. And so it's basically saying, you know, I'm going to set this contract up. Here's the public key of the lender, public key of the counter-fraud team, and the borrowers. And then the borrowers come along and, don't worry about that stuff, sign it. And it's quite simple. It just says. Now, this works because the message that the borrower has created using the client software has already signed that transaction, right? So it doesn't, this code doesn't need to worry about the signing and all that. That's just happening in the blockchain. It just needs to worry the fact that somebody can, only a borrower can call this function, right? And it's all protected by cryptographic functions, hashes. What we're doing is we're taking, like the contract in this case, is basically like the works of Shakespeare. So we've maybe got some real English contract that we want to sign, and we just crunch that into a hash and shove that in there. Remember, it's got to be the same hash. Only one hash can come out of the document. And so we put that in there too. And what this allows us to do is basically record the interactions and the validity of those into the blockchain. And only the borrowers can sign things, and that transaction can only be considered to be active if all the participants agree on it. And that is now stored in kind of like the database, the blockchain. And so what we've ended up with is a public, well, a verifiable record of that transaction. Is that making sense? For me, the kind of thing that really made me think about this was the fraud case. So it's all the other stuff, so kind of like cool. In fact, we're doing a project not dissimilar to this at Land Registry right now with digital signatures. Thing was, sometimes, let's say you're in a bank and you've got these fraud people, fraud department, whatever, and you're saying, right, okay, I'm going to give you the transaction, you're going to check it, and then you're going to tell me whether it's good or not. And I'm going to, depending on what you tell me, I'm going to record it or not in the database. That kind of depends on me writing my code right and the fraud people writing their code right and getting all that right. With this, everybody can see, everybody's using the same engine to execute the transaction. And so fraud can be very sure that they have the power to stop that transaction. They don't have to rely on any code that's being executed between the two systems. Make some sense? Maybe feel like I'm losing you a bit there. So again, so what this is doing is kind of taking the constraint. So the constraint is fraud must have seen that transaction and must agree with it. And we're commoditizing the code, if you like, for that. So rather than us having to write code, so let's assume in our organization we do 30 different types of transaction, all with different bits of software, and yet we want to be able to guarantee across the whole thing that they've all been checked by fraud. How do we do that? How do we audit that? Like literally, how do we audit it? We would have to go and check that every piece of code in those 20 different components all calls the fraud engine, right? And responds appropriately and doesn't have any bugs in it. With this, we can just go and look in the blockchain, and I was going to actually show you it working, but this is basically what's in the database, effectively. And you can see you don't really need to make some sense, but basically in there is the data of the contract and the signatures and everything. So you can now, that's just like data that's in the thing, it's spread across multiple nodes, so it's very hard to tamper with, and you can basically prove that that thing's happened. So what you're kind of getting is a commoditization of the functions of your sort of cross-functional requirements around integrity and non-repudiation and control. And it's kind of like the orchestration of that contract, the participants that all need to work in there. And that's kind of it. So that's the main point. So let's sort of recap a bit. Would you see we covered now? Does everybody have some idea about what these things might mean? It was very fast, but maybe you kind of have some of this. What are some of the things that are important about blockchain? These kinds of things. This thing about identity. So even in that scenario I was just talking about, so we've managed to sort of automate this transaction between multiple parties. Quite complex stuff to do if you were just coding it up yourself, but this gives us a sort of platform, if you like, for doing that. Identity is still really important. How do we know who people is? It's not a solved problem. Cool. So again, all kind of great, But if we're developers, why should we care about all this? Or what are we going to be doing? Are we going to be, kind of like writing blockchains ourselves, or what? And things are happening very fast. People are coming up with new tools all the time. I think this is quite a good quote. Actually, this guy works for the Eris company. And it's really likely to be about what you're going to start seeing is this sort of commoditized platform coming up. So you'll be picking it up like you do like Postgres or something like that. You'll just be getting this distributed blockchain thing. You probably won't need to know too much about all those details about hashing and public keys and all of that. It'll just happen. And you'll be getting these qualities out of that that are going to be useful to you. Like, you don't have to worry about it failing or somebody trying to subvert your stuff. Just quickly on that, if you really want to hurt your head, then this is a good paper. This is a bit about the identity and how solving that problem of the keys, right? I've got this private key, I can't give it to anybody. How does that work? What happens if I lose it? How do I generate them? It's quite an interesting thing. They're one of the companies that are doing stuff. That's kind of it. I've got a few take-home messages just to see if it's... So I think what we're talking about is the beginnings of a platform by which things can be sort of automated. Transactions, digital transactions can be automated, which is massively important when you consider that in not too distant future there will be billions of devices all around the world all doing things like your fridge will be ordering more food or whatever, or all this sort of stuff. And so if there are going to be automated things, ordering things, we need to be sure that it's all working and we can verify everything. By automating stuff, we sort of remove the need for intermediaries, so you don't really need so many people in between managing these transactions. In theory, like Bitcoin demonstrates that you don't need intermediaries to do things which are real in the world. And that's kind of one of the things that people really believe about that. An interesting idea is when you think about this as a sort of underlying transaction platform, what happens if you start putting like AI on top of that? So you have like these AI bots who can operate those smart contracts. That maybe gets a bit scary, but could happen. And then finally, like as developers, we'll probably end up using this. It'll become like a platform. And this Eris, there's a whole other talk really, probably just demonstrating Eris. But it's starting to get to that point where it's kind of quite straightforward to start getting to grips with. It's quite difficult to understand all what's going on underneath it, but the tools are getting there where you can kind of use them quite well. It's built a lot on top of Docker, so it's got a very similar syntax and use on the command line. Oh yeah, don't forget to check out the marmots. They're very cool. And that's pretty much it. Thanks. 2 minutes, I've got 2 minutes.